SNS College of Technology, Department of Artificial Intelligence and Data Science. Principles of Operating Systems. This session, we will be having a detailed discussion how Intel Pentium is been applying the concept of segmentation with paging. Let us go to the session. Let us see how segmentation takes place in Intel Pentium. A program does not directly generate a linear address. Instead, the CPU forms a logical address which is made up of two parts, a selector and an offset. The selector identifies which segment to use. It indexes into a descriptor table, either the global descriptor table GDT, which is being shared among all processors, or the local descriptor table, which is private to process, where each entry is a segment descriptor. So this particular selector identifies the segment to use and it indexes it into a descriptor table where each entry is a segment descriptor. This descriptor now contains the segment's base address, the limit, which is the size, and access or permission bits. When the selector chooses a descriptor, the CPU fetches the segment's base address from that descriptor. The offset part of the logical address is then added to the base address, which has been shown here in the diagram by the plus sign. The result is a 32-bit linear address. Before adding the CPU also checks that the offset does not exceed the segment limit and verifies access rights for protection. So we have seen how segmentation takes place in Intel Pentium. Now, here we will see how the paging architecture gets within the Intel Pentium. In this diagram, it shows that Intel's 32-bit two-level paging mechanism and that translates a linear address, that is a logical address, into the physical address using a page directory and page table which support for both the 4 KB pages and 4 MB pages. The CR3 register, that is the page directory base register in x86, here holds the physical address, that is the base address of the page directory, which is the top level paging structure. The 32-bit linear address is divided into three fields. The first 10 bits, that is 31 to 22, forms the page directory index. The next 10 bits, 21 to 12, forms the page table index, and the last 12 bits, 11 to 0, is the offset within the page. First, the page directory index selects an entry in the page directory. If this entry points to a page table, the page table index is then used to select a page table entry, which gives the physical frame address of a 4 KB page. The offset is then added to this frame base to produce the final physical address. Alternatively, if the page directory entry indicates a large page, which is a 4 MB page, the paging hardware skips the page table entirely, and in this case, the directory entry directly provides the base address of the 4 MB frame, and the lower 22 bits of the address acts as an offset. So the translation works like this. The normal pages will be the directory to the table and then the 4 KB frame plus the offset. If it's a larger page, it is from the directory to the 4 MB frame plus the offset. This hierarchical design reduces the memory usage for page tables and speeds up the address translation while allowing flexible page sizes.